So we've talked about position, velocity, and acceleration, and now we want to talk about actually bringing them all together and doing kind of the math that describes motion. So some key concepts and assumptions before we get started. First, there's 4 key variables, and second, the acceleration is constant. That's because we're only going to do calculations with constant acceleration. If there's a changing acceleration, it's really hard to do math calculations without calculus. It's pretty easy if you've got calculus, but this is an algebra-based course, so we're only going to be dealing with constant acceleration as far as our calculations go. It's totally possible you get asked a question that asks you to consider what would happen if acceleration is changing, but you wouldn't have to do any math for that. All right, so there are 4 kinematics equations, and these come on your equation sheet except for this first one. So I'm just going to write it down first. And we have delta x equals the average velocity times the change in time. So this is our first kinematics equation. There's not a specific order. This is just the order that I'm writing them because the order I'm going to derive them in. But this is the first one we'll talk about. The second kinematics equation we're going to talk about here, and I'm just double checking because I want to make sure it's written the same way as your equation sheet. V equals V naught plus A delta T. Now technically this should be a bar, but because we're always dealing with constant accelerations, the average acceleration is the same as the whatever the acceleration is at any given moment. So that's why we don't need that bar if we're assuming constant acceleration. Third, we're going to look at x equals x naught plus v naught delta t plus 1/2 a delta t squared. And then lastly, our fourth equation is going to be v squared equals v naught squared plus 2a delta x. And again, technically these a's are only true if they're talking about the average acceleration, which is why, but we've left it off because, again, convention of how the AP test handles it. But these are the 4 kinematics equations. They're the ones that we'll be looking at. These bottom 3 are on your equation sheet. The top one, though, is just basically the definition of velocity. So let's go and quickly derive those so you can see where they come from and why we have them. I don't expect you to be able to derive these yourself. You don't need to know this as far as for the AP test, so feel free to just watch and not take notes. But I do want you to see where they come from to see that there is a reason and they're not just made up out of nowhere. So derivation 1, we're trying to derive the equation delta x equals v bar delta t. Well, we know that the average velocity was defined as delta x over delta t. This is a definition. And so it's a pretty trivial derivative or derivation, just like so, just rearranging it algebraically. 1 down, 3 to go. Equation 2 is a little more involved, but not terribly much so. V equals V naught plus A delta t. So with this one, we're going to start with our definition of acceleration, or an average acceleration. A bar equals delta v over delta t. But again, because we're assuming average acceleration, or assuming acceleration as a constant, the average is the same as the acceleration. So that's where we get A equals v delta t. And then we can write A times delta t equals delta v. Remember that delta is just always final minus initial. And so we can just do a little more algebra to get the form presented above. So this is basically rearranging the definition of average acceleration. Now we get into some of the longer ones, and this is actually the longest one, but it just takes building blocks we already know to work towards the equation x equals x naught plus v naught delta t plus 1/2 a delta t quantity squared. So for this one, we're going to start with what we had defined earlier. So v equals v naught plus a delta t. So we're starting with what we had on the previous slide here, starting with this right here. And then what we're going to do is a little bit of fancy math. We're going to add v naught to both sides. And then we're going to divide both sides by 2. So v plus v naught on the left side over 2. 2 v naughts divided by 2 gives me just v naught. And then 1/2 a delta t. So all I did again was divide both sides by 2, and then I did some simplification algebra on the right here. From this point forward, there's this little bit that we didn't talk about, but if acceleration is a constant, the average velocity is just the final velocity minus the initial, or final velocity plus initial velocity divided by 2. And this is something that if you want me to walk through it with you individually, or if we want to walk through it as a class in person, I'll explain why this is true. But just know this is true for constant A. So that means I can replace this left-hand side with v bar equals v naught plus 1/2 a delta t. And then if we remember back from earlier, v bar is just delta x over delta t. So coming back here, we can write delta x over delta t is equal to v naught plus 1/2 a delta t. So then I can rearrange that to get delta x equals v naught delta t plus 1/2 a delta t. As a reminder, any delta is going to be the final value minus the initial value. And I'm going to leave that kind of scribbled for now. But that lets us then rearrange algebraically to get x equals x naught plus v naught delta t plus 1/2 a delta t squared, which is in fact what we had up top. 3 down, 1 more to finish off. So for this one, we're going to start with x equals x naught plus plus v bar delta t. So let me undo that. And this is again just that first equation we used. With some kind of cleaning up, simplifying. And our goal here is to get to the equation v squared equals v naught squared plus 2a delta x. So if we have this initial, we're going to use some substitutions. We already said that v bar is v plus v naught over 2 if the acceleration is constant. And we're going to use the substitution that delta t is equal to v minus v naught over a. And this is just from rearranging the a equals delta v over delta t. So if you need to pause to see why this is true, go ahead and just make sure those match. Anyway, coming back over here, x equals x naught time plus v naught over 2 times v minus v naught over a. I'm going to clear things out, move to the left-hand side, some of these things. So I multiplied the 2a to both sides, and I subtracted the x to the other side. So then I get 2a delta x equals v squared minus v naught squared, because when you FOIL or distribute this, that's what you end up with there. And then some algebraic rearrangement later, we end up with the following, which is the equation that we started with. So one thing to jump to real quick, coming back here. A significant thing to notice about each of these equations is each equation has 3 out of the 4 variables. And what 4 variables are we talking about? We're talking about x, velocity, time, and acceleration. So this first equation, it is missing a. The second equation is missing x. This third equation is missing v. And this fourth equation is missing t. So that's why these are all useful, is because they all only require 3 out of the 4 values that we have. Now I know some of you might have seen this and said, wait a second, what about that v naught? We're talking about final values. So a, x, v, and t, not initial values. So yes, this third equation is a little weird, but it does still stand. You don't need velocity, you only need the initial velocity there. So then next we'll talk about some problem solving.